Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we went through various modules, and this is the 12th module that we are going through on overmodulation. So, in the last lecture on overmodulation, we reviewed sine triangle PWM and we reviewed average pole voltage and average line client voltage in an inverter. Like basically this pole voltage is the voltage at the midpoint of a leg measured with respect to the DC bus midpoint. Average pole voltage would mean the pole voltage averaged over a carrier cycle. Similarly, this line to line voltage is the output between the two output terminals of the inverter, say R and Y, and that is averaged over a sub cycle or a half carrier cycle. That is what you call as average line to line voltage. Similarly, if you consider a 3-phase star connected balanced load, you can look at the line to neutral voltage on the load, and you can take its average value over sub cycle or half carrier cycle, and these 3-phase load voltages can be transformed into the space vector domain, where they would have two components and they would be the 2-phase voltages. So, we reviewed these, and then we started analyzing sine triangle PWM during overmodulation. We looked at how does the average pole voltage vary. For example, the variation in average pole voltage will be just sinusoidal in sine triangle PWM if it is linear modulation. If it is overmodulation, it is sinusoidal, but it is a peak clipped sinusoid. So, correspondingly the average line to line voltages are no longer sinusoidal, they are also non sinusoidal. There are low frequency harmonic contents here, and again the line to neutral voltage is low frequency harmonics and is non sinusoidal. So, this 3-phase line to neutral load voltage, it can be transformed into 2-phase voltages, and they are also having low frequency content, harmonic content. And then we started looking at the magnitude and angle of the average vector. So, what we found was that the magnitude of the average vector actually starts varying initially, that is when it gets into overmodulation. When the converter slightly into overmodulation, there is not so much variation in the angle of the average vector continues to move more or less linearly with time, but the magnitude starts varying significantly. And subsequently, when we come closer to the 6-step operation, what we find is the angle also starts varying significantly. I mean, the angle no longer moves linearly with time. So, it is the angular velocity is sometimes 0 and sometimes it is faster than the fundamental angular frequency. So, the angle versus time, it appears to be a piecewise linear function, that is what we saw. So, today what we would do is we would actually quickly review this part of sine triangle PWM, and our emphasis would actually be on conventional space vector PWM. We would first look at conventional space vector PWM as a common mode injection PWM, that is you have 3-phase sinusoidal signals and you can add a suitable common mode component, which will ensure that this common mode component will ensure that your null vector time is divided equally between the 0 states, and that is what is conventional space vector PWM. We will view that, or we will rather review this also, and then we will analyze conventional space vector PWM during overmodulation, just as we did for sine triangle PWM previously. We will do that for CSV PWM now. So, we will look at the average pole voltage and average line to line voltage during overmodulation, like what we did for the sine triangle PWM. We will do the same thing for the space vector PWM. So, and we will look at the 3-phase line to neutral voltages, and we will look at the 2-phase line to neutral voltages after transforming them into the space vector. So, these 2-phase voltages in the space vector domain can be converted into the magnitude angle form. So, this you can say it is in the so called rectangular coordinates, you can convert it into polar coordinates, so that you can start seeing the magnitude and angle of the average voltage vector. So, today we will look at how does the magnitude of the average voltage vector vary as the inverter goes into overmodulation. Similarly, how does the angle vary? So, these are certain things we will see. We will see that there are good similarities between sine triangle PWM and conventional space vector PWM during overmodulation, while there are also some differences. This understanding of how these converters behave, that is analysis of the voltage source inverter operating with sine triangle PWM or conventional space vector PWM during overmodulation, will help us understand how we can implement overmodulation in space vector terms. So, we will look at what is known as two zone overmodulation algorithm. We will also try to quickly see, like, there are some alternative overmodulation algorithms. There is a standard one, there are also other things. We will see if we can do some analysis in this synchronously revolving reference frame. Otherwise, in any way this would be, you could also look at the references. I will give you references for, I will indicate references for all this. The references would certainly talk about these things in good detail. So, let us get started with understanding overmodulation. So, I am calling it overmodulation in space vector modulated inverter. What I am looking at is I am looking at a voltage source inverter, and I am looking at conventional space vector PWM. So, the conventional space vector PWM can be implemented by adding a certain common mode signal to the 3 phase modulating signals. That is what we are going to look at initially. Then we can look at its implementation from the space vector point of view also. So, alright. So, this is a voltage source inverter, and this is the pole, single pole double throw switch. This is the pole. The voltage at the pole measured with respect to O is pole voltage VRO. Similarly, you have pole voltage VYO, you have pole voltage VBO, and you always have line to line voltages VRY, VYB and VBR. And if you consider the load, which is not shown in the picture, as a 3 phase star connected load with a neutral point N, then you also have VRN, VYN and VBN. Alright. So, now if you modulate it with sine triangle PWM, now you have a sinusoidal 3 phase sinusoidal signal, its peak is 0.8 times the carrier peak. So, you have some 3 phase signals like this, and you compare it with the carrier. When the sine is greater than the carrier, the top switch of a leg is on. When sine is lower than the carrier, the bottom switch is on. That is the convention we have been adopting. And if you do like this, what happens? You have your average voltages like this. These are the 3 phase modulating signals. The average pole voltages are directly proportional to this, the modulating signal. So, it is basically these two are only scaled versions of the other. You normalize your MR with respect to Vp, multiply by VDC by 2, you will get your average pole voltage. So, you would get sinusoidal average pole voltages in linear modulation. Again, you are going to subtract 2 sinusoids, that is going to result in another sinusoid. These are 2 sinusoids of the same frequency, phase shifted by 120 degree. So, the resultant would be a sinusoid of the same frequency, but this will be root 3 times, its amplitude will be root 3 times this amplitude, and it will be phase ahead of VRO by 30 degrees. Then you can come up with VRN average. This is the line to neutral voltage on the load. R stands for the load terminal, N stands for the load neutral. So, VRN is the load to neutral voltage, the load phase to neutral voltage on the load. This you can arrive at by subtracting VRY average minus VBR average divided by 3. So, once again, these two are sinusoids and their difference would be a sinusoid. And when you are doing, this would give you, when you subtract this from that, its amplitude will be root 3 times that of VRY, and when you divide it by 3, so this amplitude for VRN would be the same as the amplitude of VRO. So, we have VRO sinusoidal, VRY will also be sinusoidal, its amplitude will be root 3 times that of VRO, and when you do VRY average minus VBR average, you will get something which is whose amplitude is root 3 times that of VRY or 3 times that of VRO. Since you are dividing it by 3, you will get an amplitude for VRN average which is same as VRO average. So, what you will find is, there are sinusoids, this is sinusoidal, this will also be sinusoidal. So, this is what you get here. So, for sinusoidal PWM, when common mode is added here for MR, and that common mode will also be seen in VRO, the story is slightly different as we have seen before. So, it is MR, MY and MB are sinusoids, the common mode is added. So, that becomes MR star, MY star and MB star. And now VRO average is MR star into VDC by VP, it goes on like this now. So, as I have mentioned before, here VRN average is not equal to VRO average, because VRO average would have fundamental plus the common modes. Here this will have only the fundamental component, the triplet frequencies will go away. During linear modulation, all this will be alright, you will get MR star. So, your VRY average and VRN average will be sinusoidal, but what will happen when you go into overmodulation, that is when MR star goes greater than VP, this will get clipped to plus VDC by 2. When MR star goes below minus VDC, it will get clipped to minus VDC by 2, and therefore, your VRO average will be a peak clipped waveform. So, that is what would result in distortions as we had seen yesterday. Now, once you have this VRN average, VON average and VBN average, you can transform them into the space vector domain. So, this is V alpha average and V beta average. You can further square this and also square this and add the 2 and take a square root, that would give you the magnitude of the average vector. And also you can say you can divide V beta average by V alpha average and take the inverse tan of that, that can give you the angle of the vector. So, you can also convert this, here a vector is in the rectangular coordinate system, you can look at this in the polar coordinate form and you can get the magnitude and angle also. So, if you look at this magnitude and angle, when your inverter is modulating in the linear modulation, what will happen is every subcycle it will apply some average vector, that average vector's magnitude will be equal in all the subcycles at steady state, and this angle difference between the two, that will be omega times Ts, where Ts is your subcycle duration and omega is your fundamental angular frequency. So, these angle will be uniform. So, it is like the average voltage vector moving at a uniform angular velocity and having a constant magnitude. So, these would change when you go into overmodulation. Now, when you are looking at space vector based PWM, what you are trying to see is there is a revolving vector, and the revolving vector you are sampling in every subcycle Ts, and you get some vector which is your reference vector. You try to do synthesize this by time averaging V1, V2 and Vz. So, how do you do that? As shown in the equation, you apply V1 vector for T1 given by this, you apply V2 vector for T2 seconds given by this equation, and Vz vector for Tz seconds is given by this equation. So, you will be able to get an applied voltage vector which will be equal to your reference voltage vector in an average sense. So, in conventional PWM what do you do? This null vector is applied using both the 0 states and both are applied for equal durations Tz by 2 and Tz by 2. You stay here for Tz by 2 and go here for T1 seconds, move here, go to T2 seconds and come back for Tz by 2 seconds, and you do the reverse now as we have seen before. So, same thing is shown here 0, 1, 2, 7, 7, 2, 1, 0, and T7 is equal to T0 is equal to 0.5 Tz. This is what is conventional space vector PWM. Here you are trying to implement it from the space vector point of view. What do you want to effectively achieve is that T0 and T7 should be equal. So, you can achieve this by common mode addition also. Let us say you have MR, MY, MB. The maximum out of the 3 is taken as M max, the minimum out of the 3 is taken as M min, the middle value out of the 3 is taken as M mid. So, M max would be the highest one, M min would be the most negative one, and M mid will be close to 0, will be closest to 0. If you take the unsigned values, M mid will have the lowest value. So, you call them M max, M mid and M min. Now, you add certain common mode voltage, let us call it MCM. So, that you add it M max, M mid and M min. So, you get M max star, M mid star, M min star, which are the modulating signals you are going to use. Now, if you want your null vector time to be equally divided, then you need this condition M max star and M min star should be equal in amplitude, but opposite in sign. They should be equal in magnitude, but opposite in sign, or M max star plus M min star is equal to 0. So, if you need that, then M max plus M min plus 2 MCM is equal to 0 as we had done before, and this gives you the expression MCM is minus 0.5 times of M max plus M min. And now, M max plus M min is equal to minus M mid, because you start from 3 phase sinusoidal signals, and therefore, MCM is equal to 0.5 M mid, which is what we have been using. So, you can actually by if you have 3 phase sinusoids, you can generate common mode like this, and you can add it to all the 3 signals, and then you do your triangle comparison and generate your PWM. So, this will ensure equal division of null vector time. This is an easy way of implementing conventional space vector PWM rather than going through the space vector approach, where you have to have a revolving vector, you have to find out which sector it is in, and then you have to calculate T1, T2 which involve trigonometric functions, and so there is some computational complexity involved. Whereas, here this is a simple comparison which can be implemented in many timer based implementations, where it is easy for you, like in DSP and all that, where it is easy to implement here. So, you use this triangle comparison approach, and you see that by this addition you get 15% higher voltage also than sine triangle PWM, etc. So, this is something we had seen before. Now, that is what we are going to use now. But what we do is, if you have MR, MY and NB of amplitude peak value 0.8 times the triangle, we are adding common mode. So, the common mode signal is this blue signal. When you add that, what happens, this MR becomes this MR star as shown by this line, and you can see that the peak value of MR star is significantly lower than the peak value of MR. So, this increases your DC bus utilization. So, if your MR goes to 1.15, your MR star just touches 1. 1.15 more precisely is 2 by root 3. So, or reciprocal of root 3 by 2, which is sine 60. So, you see that here it touches 1 and MR star just touches 1, whereas MR is the peak value of MR is actually higher than 1, that is 2 by root 3. So, this is what is responsible for the 15% higher DC bus utilization, and so this is conventional space vector PWM giving you higher DC bus utilization. So, there are, as I have also discussed this already, but this is just a quick review of that. So, there are good references. This is a good paper on this, where it talks of the null vector time division and how the different things are I mean PWM methods, continuous and discontinuous PWM methods, you get a discussion on that. So, you use the 3 phase modulating signals to find out your active vector time, etc. So, this is a good reference. This is another reference which also talks about how do you generate common mode in the various cases for continuous and the discontinuous PWM methods. And this is a tutorial paper essentially on this conventional space vector PWM, how you can view at conventional space vector PWM as a modified form of sine triangle PWM. So, now we are going to look at this CSV PWM as a common mode injection PWM for this part of that. So, before that we would have to review what we did in the last class on analyzing the sine triangle PWM. So, let us say we take 1.1 3 phase sinusoids of amplitude 1.1 times the peak of the carrier. So, it goes into overmodulation. So, what happens? The VRO average is clipped, it is clipped to 0.5 VDC, it is clipped to minus 0.5 VDC, VYO average and VBO average are similar, just phase shifted by 120 degree and 240 degree respectively. So, what happens? You get your VRN average. So, from VRO minus VYO you can do, and then you can come to VRN. So, your VRO average is shown by the blue line and VRN is shown by the red line. There is a small difference between the two. As I mentioned yesterday repeatedly, that VRN average would not contain triplen frequency components, whereas VRO average would contain. If VRO average had been sinusoidal, it would contain nothing, but once it is peak clipped sine, it will have third, fifth, seventh, all these harmonics, and the red waveform will not contain third, ninth, etc., but it will contain fifth, seventh, 11th, 13th, etc. So, the red waveform is your VRN average. Similarly, you will have VYN average and VBN average. If you transform them into the space vector domain, you get your V alpha average and V beta average. You can clearly see that these are not sinusoidal, there is considerable distortion here. All right. So, if you look at the magnitude of the vector, it is a little above 0.785, which is pi by 4, and here you find it is close to 0.8, it goes a little above and below that. So, the magnitude varies, this is how the magnitude varies over a sector, and this repeats over every sector. And how does the angle change? The angle change from 0 to 60 degree of the vector. So, the average vector continues to move linearly with time, its angular velocity continues to be constant, whereas the magnitude is a little, it changes, it goes up and down, I mean it varies. So, this is at m is equal to 1.1. You go in deeper into overmodulation when you go a little deeper into m is equal to 1.2. Now, you see that you are going above this for a considerable length of time, which is much longer than 60 degrees, you are going into overmodulation. So, and also when it is overmodulation, R phase is in overmodulation here, or R phase modulating signal is exceeding positive carrier, B phase is exceeding, going below the negative carrier here. Similarly, when R phase is exceeding the positive carrier here, the yellow phase is going below the carrier here for a short while. So, these kinds of things happen, and you also see the clamping duration is longer, you would find 2 phases clamped concurrently at times. Now, you have this VRY average, which is the VRO average, average pole voltage, the blue waveform, and this is the VRN average, that is the average phase to neutral voltage applied on the load, that is the red voltage. The red voltage does not contain triplen frequency components, and that VRN average, the red voltage, you have similarly you would have VYN average and VBN average. We transform them into the space vector domain to get your V alpha average and V beta average. V alpha average would have the same wave shape as VRN average, just a scale factor of 2 by 3. All right. So, you have this, you see that there is more distortion than we saw before, and you can see that the magnitude has increased a little. Earlier it was going below 0.8 and above 0.8, now it is all above 0.8. So, the average value is above, well above 0.8, but you see that there is a clear error in the magnitude, which is very visible. It is low and it is high, and the variation in the magnitude is more clearly visible than at m equals 1.1. The angle continues to be more or less linear with time of the average vector. So, what we can say is, you have a situation where we are applying vectors like this, Let us call these Vref1 as a vector which we are applying in one subcycle, Vref2 as the vector we are applying another subcycle, Vref3 as the vector we are applying in the next subcycle. What we have is, as I said yesterday, Vref1 is not actually equal to Vref2. Again, that is not equal to Vref3. There are variations in that. However, this angle and this angle, they are equal. These are equal to omega ts roughly. This is the scenario that you have here when you are doing overmodulation with sine triangle PWM. So, you will see that it is improved when we go into conventional space vector PWM. It is a little different from here. There will be variation in the magnitude, but it will follow the hexagon and the circular trajectory. Before that, let us look at that one, this sine triangle PWM, two ranges, one between 1 and 1.15. So, here at any time only one phase modulating signal will go above or below the peak, carrier peak, and the other range 1.15 to 2. In this you would find two of them going above. Sometimes only one modulating signal would go above the carrier peak, and or sometimes you would have two of them going beyond the carrier peak, one above the positive carrier peak and one below the negative carrier peak. So, these two ranges if you look at, what do you see? You see that the low frequency distortion is quite pronounced in the output voltage, inverter output voltage, be it pole voltage, line to line and the phase to neutral. The main difference is in the pole voltage you may have triplen components and phase to neutral you will not have, that is the essential difference. And these phase to neutral voltages, those are 3 phase voltages, can be transformed into the space vector domain. And if you look at the magnitude of the average vector, that varies with the fundamental angle. The trajectory is not circular. That average voltage vector applied in various subcycles, if their magnitude are equal, the trajectory of the tip of the vector would be circular. Now, it is non-circular. However, the angle of the average voltage vector varies almost linearly with time. There is not a very appreciable change. If there is some change, but that could be ignored. So, now let us say if you go into m is equal to 2, which is that end of what I said here. So, when you go to m is equal to 2, what you find is for 120 degrees this R phase carrier signal, modulating signal is above the carrier, positive. Here for 120 degree it is below the negative. So, that is at 30 degrees itself it crosses 1. So, from 30 to 150 degrees it is above the positive peak. Here again from 210 to 330 degree it is below the negative peak, and therefore, your average pole voltage for R phase is like this, looks like a trapezoidal waveform because this part of the sinusoid is more or less a straight line. And so, you have the average pole voltages for the Y and the B phases now. So, two phases are clamped concurrently, R and Y phase, R and B phase, Y and B phase, Y and B phase. Here B and R phase, I mean this is Y and R phase, B and R phase. So, at any instant you find that any carrier cycle you will see two of them are clamped. So, your resultant, this is the average pole voltage for R phase. The average line to neutral voltage for R phase applied on the load is a little different like this. And so, because this red waveform does not contain the triplen components, it looks a little closer to the sinusoid. So, you can see this now. So, you can transform that VR and average. If you look at the voltage vectors, the two components alpha and beta axis components of the average voltage vector, the alpha component looks like this and the beta component looks like this. Okay. So, if you look at the magnitude, you can see that there is a significant reduction in the magnitude. Sometimes the magnitude becomes equal to 1. 1 stands here for VDC, that is here the active vector is getting applied, and once again the active vector is getting applied here. So, if you look at the angle is still more or less a straight line. You can actually plot a straight line from here to here and you may find a small variation, but that variation can actually be ignored. So, you can still see that the angle varies. The angular velocity of the average voltage vector is still more or less a straight line now. But now what happens, as I said, the 0 vector is never getting applied. Two of the phases are always clamped. So, which two phases can be clamped? If you look at here, Y phase can never be clamped in sector 1. On the other hand, R phase can be clamped and B phase can also be clamped. So, what actually is happening is you are applying voltage vector like this in one subcycle. In the next subcycle you might apply a voltage vector like that. So, this is in the third, this is in the subsequent ones. So, the voltage vectors, the average voltage vectors applied are all like this. They all go and touch the tip just touches the hexagon. So, what happens? To produce this vector you are not applying null vector, you are only applying active vector 1 and active vector 2 for different periods of time. Only one phase switches mainly this phase switches now. Okay. So, the trajectory when you go into this m is equal to 2 is entirely on the hexagon. So, at this point of time, if you see the voltage percentage you will get would be like 95.2% of the 6 step voltage is what you will get. Analysis will show this. This is there in the references also. Alright. So, what do you find at m is equal to 2? Two modulating signals always exceed the carrier peak in any carrier cycle. Only one phase switches. This is switching between the two active states. So, no 0 state is applied. Pulse dropping for 120 degree in each half cycle for each phase. You have a high low frequency distortion and magnitude of average voltage vectors varies, but now the trajectory of the tip of the average voltage vector is hexagon. But you still find that the angle of the average vector is almost linear with time on the fundamental. So, when you go beyond this, this would start changing now. So, if you look at m is equal to 3, it has crossed the carrier peak here itself and it goes well above that. So, it is a very short interval that it is within the carrier peak. Here again it is for a short interval. So, R phase will switch here, will switch here, R phase will not switch between this. Again it will switch here and it will switch here, it will not switch in this interval. So, your pole voltages would look like this. The average pole voltage is equal to 0.5 VDC for a duration longer than 120 degrees. Here it is equal to minus 0.5 VDC for a duration longer than much longer than 120 degrees. If you look at your average pole voltage, it is like this. The average line to neutral VRN average is like this. Similarly, you will have VYN average and VBN average. You transform them into the space vector domain, you get your V alpha average, you get your V beta average. So, you can see V beta average is flat for a very long time and you can see V alpha average is also flat. So, when the two are flat, what does it mean? V alpha average is also constant, V beta average is also constant. Actually, that means that the vector magnitude is constant. So, V alpha average is 1, V beta average is 0, 1 square plus 0 square under root is 1. So, what is happening is you are actually applying the active vector, incidentally it is the active vector 1 and that is what is applied in all the subcycles in this region. And you look at here, what you have is actually 0.866 root 3 by 2, what you have is 0.5, you square this plus you square this, you will get again 1. So, you are applying here again the vector magnitude is 1, you are actually applying active vector 2, here you are applying active vector 3, that is why your V alpha average and V beta average are constant over those subcycles now. So, this can be clearly seen in here. This is only sector 1, this corresponds to the start of sector 1 where R phase is going to the positive peak. So, from 1 to here it is about little more than 10 degrees, vector 1 is applied, the last 11 degrees or so vector 2 is applied. The same story in sector 2. Sector 2 in this portion active vector 2 will be applied, here active vector 3 will be applied and so on. So, what happens to your angle? This, since only active vector 1 is applied for up to little more than 10 degrees, the angle is 0. Again for the last 10 or 11 degrees in this sector, the angle is equal to 60 degree, it is constant. In between it rises. Obviously, this is faster than the fundamental angular velocity. If you look at the fundamental angular velocity, it will actually the fundamental average voltage vector will actually be going like this. But when you are looking at the average voltage vector, that is you are looking at the voltage vector averaged over every subcycle, that vector really moves like this. So, you can actually approximate it by a piecewise linear function, 0 here and rises at some velocity here and I mean with some slope here and again constant here, you can approximate it with piecewise linear thing. So, what really happens here is you have active vector 1 is applied in one subcycle, this is repeats. In a number of subcycles you would apply active vector 1 only, then you will apply some vectors like this, the vector will go on changing. Again you will go to active vector 2 and for certain duration you will continue to apply active vector 2, then it goes in here. This is how the average voltage vectors are in different subcycles. So, if you look at it here, what you get is two modulating signals exceed the carrier peak and for m greater than 2 everywhere and sometimes only one, sometimes even all three would exceed that 2 minimum and sometimes it could be even 3, which is what you have to make sure here. So, I will probably indicate that here itself. Okay, right. So, this whenever there is a switching, that switching is between active states and no 0 state is ever applied, and pulse dropping is for more than 120 degrees and the distortion is very high. The trajectory of the tip of the vector is hexagonal, it is always on the hexagon. The angle of the average voltage vector varies in a piecewise linear fashion with time, and this is important because actually in the space vector domain, this is the understanding we will use in coming up with an algorithm for a space vector modulated inverter. And what you also find is the average voltage vectors applied in different subcycles are kind of concentrated around the active vectors. What I mean is, if you look at this, you see that there are many here. So, you will have voltage vectors here, but you have lot of vectors. Yeah, in this particular case you have many vectors actually along active vector 1 itself. So, eventually what happens is the depth of modulation goes on increasing, more and more vectors will start coming close to this and will be aligned along with the active vector 1. Again, among these vectors, more and more of these vectors will get aligned along active vector 2, and finally when you reach the so called 6 step mode, you would have all the vectors in the first 30 degree of the sector applied along here only, and the next 30 degree you would have all the vectors applied here only, and again first 30 degrees in sector 2, all the vectors, average voltage vectors will be along active vector 2 and so on and so forth. So, all this will come closer and more vectors will come and merge with this active vector 1 as modulation depth increases. So, you can actually find these details, this analysis of the sine triangle PWM from a space vector point of view. What happens to the average voltage vector, how does it vary? In this master's thesis about I think a chapter of the thesis covers this, and this was also presented in a part of this was presented in a conference paper, and this is a more full length journal version in which you will find for sine triangle PWM, and also you will find for the common mode injection PWM now. So, let us look at it's the analysis of the overmodulation in the CSV PWM is pretty similar to that of sine triangle PWM. We are looking at it as a common mode injection PWM. So, when you are looking at so called m is equal to 1.15 or 2 by root 3, you see that the MR star is just touching 1, which is the peak carrier, it is not going above that, it is not going below. So, you are into linear modulation, so there is no problem. So, you have your average these are the 3 phase voltages, average pole voltages, and you look at the line to line voltages, the line to line voltage, the average voltage just touches VDC, which is equal to VD 1 stands for VDC. So, you have nice sinusoidal voltages, and the line to neutral voltages on the load VRN average, VON average and VBN average are also nice sinusoidal waveforms, and incidentally this peak value is what? It is 0.577, that is 1 upon root 3. Okay. Now, what you have here is this VRO average, it has a peak value of 0.5 VDC and this is 0.577 VDC. Again at the expense of repetition, I would say that whatever triplen components are here, you subtract them, you are actually getting this now. So, you are able to pack a higher fundamental voltage of 0.577 VDC into a modulating signal whose peak does not exceed 0.5 VDC. That is what you are achieving now. So, here what happens, you are looking at the average pole voltage. So, if you look at what are the different average vectors which are actually produced, what you will find is, you will find their tips to follow a circle like this. Their tips will actually be following at this modulation index. You do the analysis as we did for sine triangle PWM before. So, what you will find is, you will find that subcycle by subcycle you will get an average voltage vector whose magnitude is constant and it will vary like this. So, this magnitude is equal to 0.866 VDC for our convention, and this angle is omega TS, the angle between average vectors of any 2 consecutive cycles is omega TS. This is the situation when you have conventional space vector PWM and its modulation signal m is equal to 1.15. So, I mean that is the thing. Now, we go above that, from 1.15 we go to 1.2. So, we see that for a small region the CSV PWM's modulating signal goes above that. Here it once again here it goes above the peak, and in sine triangle PWM you would have found that it went above, I mean only here, but here it goes above here and also here. that is around 60 degree and also around 120 degree. The same way look at the negative half cycle, R phase modulating signal is going below the peak here the negative carrier peak, here also it is going below the negative carrier peak. Okay. So, in these are regions where you are going to get clamping for R phase and similarly for the other phases now, and that is what happens. This is pulse dropping. There are no pulses, while there are pulses here, the R phase switches here, it does not switch here, the pulses would be missing. So, it is called pulse dropping. You have pulse dropping here and also here and here for all the phases now. So, the same kind of analysis is still valid. If you calculate your VRY average, it will look like this. Now, you can see that VRY average is equal to VDC. VRO average cannot exceed VDC by 2, VRY average cannot exceed VDC. Why? Because VRY, the instantaneous value, the maximum value is only VDC. If you apply VDC throughout the subcycle, you are going to get plus VDC. Similarly, VRY average can also not go below minus VDC, because if it is minus VDC is applied throughout the subcycle, you get minus VDC. You cannot get anything lower than this, you cannot get anything higher than this. So, you see your VRY average is clipped like this, and you can see there is a significant amount of distortion here. Now, you go into VRN average, you do not see any clipping here, because the triplet frequency components have all been subtracted and all that so on, but you see that it goes well higher. You can see that it goes well higher. This is V alpha average and V beta average, of course. So, it has a tendency to go closer to 1, it will reach somewhere close to 1. You take it as 0 here, at the same time it is 0, V beta average is 0 and this value is something like 0.9. So, the vector is something like 0.9. So, you are actually approaching 1. Alright. So, if you look at the vector, the magnitude of the average voltage vector, it is constant and then it varies, it is constant and it varies, it is constant, it varies. So, it has a periodicity of 60 degree every sector. Well, let us talk about sector 1, which starts from 90 degrees where R phase has positive peak and ends with 150 degree where B phase has its negative peak. So, initially you find that it is constant, that is active vector 1 is applied here and here active vector 2 is actually applied. So, that is what happens now. So, now if you look at only one sector, you can see that more clearly. Here it is active vector 1 applied, active vector 2 applied, and here there is some switching between active vector 1 and active vector 2, and the magnitude varies like this now. So, if you look at the fundamental angle, I mean the angle of the average voltage vector, it is same as the fundamental angle, it just rises linearly. So, the angular velocity continues to be constant now. So, what do you get here? So, you would have some places where we are looking at some modulation index of 1.2. What you will find is, you will find that there are some places where you may have some vector applied and there are some other places where you may have find some vectors applied like this. If you go back, you will see that there are some place here, for example, here only one phase switches are take here, only Y phase switches, whereas B, R and B are clamped. So, this is a case where only the active vector is switching, and in this case there is no 0 vector applied and the average vector tip will be touching the hexagon. Whereas, you take here R phase is switching, Y phase is also switching and B phase is also switching. So, these are places where all the 3 phases are switching and therefore, the 0 state is also getting applied, though to a lower though the duration of application of 0 state would be lower now than it was during linear modulation. So, here you find all the 3 are applied. During this time what happens? It actually follows a circular projection of the trajectory. What happens here is, this follows a circular portion. In this part it goes like that, like this. So, once again what you will have here is, you have it like this. So, the trajectory is partly on the hexagon and it is partly on the circle. It is partly on the hexagon, it is partly on a circle, partly on hexagon, partly on circle. This is how the trajectory looks for you. This is how the trajectory looks. Okay, let us go further. This is something we are trying to summarize that. there is no modulating signal or two modulating signals exceed the carrier peak in a given carrier cycle. So, if you know if no modulating signal exceeds, all three phases switch and you are on the circular portion of the trajectory, otherwise only one phase switches, and that is the switches between the active state and you are on the hexagonal portion of the trajectory. You can see pulse dropping around the two peaks of that, and then there is a lot of low frequency harmonic distortion, and you can see that the magnitude of the average voltage vector varies with fundamental angle. The trajectory is partly circular and partly hexagonal, and the angle of the average voltage vector varies almost linearly with time or fundamental voltage. So, you can see that there is some similarity and dissimilarity here. In the case of sine triangle PWM, we found that the voltage was varying when you went into overmodulation, but it was not really, the magnitude was varying. Here also the magnitude is varying, but there is a clearer pattern in the magnitude variation here. It is circular, hexagonal, circular, hexagonal, it is following the trajectory like that. The next one, so there is some similarity, there is some dissimilarity. Again, when you are into overmodulation in sine triangle PWM, up to some extent, that is when you have not gone close to 6 step operation, your movement of this is linearly with time, mean the angle varies linearly with time, the angular velocity is almost constant, which is also true here for conventional space vector PWM. So, this was non-circular here in sine triangle PWM. Here you have it as partly circular and partly hexagonal. In this case there is a similarity, you see that it is almost linearly with time, the angle varies almost linearly with time. So, you see that there is a great amount of similarity here. So, initially during overmodulation, what happens is only the magnitude of the vector starts varying, the angular velocity continues to remain uniform, but then that will soon change now. When you touch m is equal to 1.33 with CSV PWM, what you find is for an entire 120 degrees, you are above the peak of the carrier, and therefore, the phase is clamped for 120 degree here and it is clamped for 120 degrees here. So, you have the 3 phase pole voltages like this. So, this is similar to what we had for m is equal to 2 for sine triangle PWM. The same average pole voltage we got for m is equal to 2. At m is equal to 2, you will have a very similar kind of maybe only a small difference will be there in this one. That would have been a sinusoidal wave, there is some sine with some common mode added here. So, you will would have had a very similar average pole voltage when you considered m is equal to 2 for sine triangle PWM. So, this is how the average pole voltage looks roughly trapezoidal, and this is how the line to line voltages will be. They also look trapezoidal, but the duration of clamping is lower. So, here this means basically R and Y are both clamped concurrently here. This means that Y and B are both concurrently clamped here. This means both B and R are concurrently clamped in this interval. So, if you look at that, you can see that these are hexagonal waveforms. This is V alpha average and V beta average. So, the two components of the average voltage vector in the stationary reference frame, this is V alpha average and this is V beta average at 1.33. So, this is VR average and this is VRN average, to emphasize the point. So, very similar to what it was at m is equal to 2 with sine triangle PWM. So, now what I am going to do, look at the voltage vectors, they vary like this over every sector. If you look at the variation over only one sector, the variation is like this, and if you look at the angle is still linear. This happens up to 1.33, it happened up to m is equal to 2. In both the cases, what you should remember is the fundamental voltage is similar. How much is the fundamental voltage? The fundamental voltage is 95.2% of the 6 step voltage. I will say 95.2% of the 6 step voltage. So, if you look at this, what happens? The average voltage vector would touch the tip. Next subcycle also it will touch the tip. Next sector also it will, next subcycle also it will touch the tip. So, it will be like this. This is how the average voltage vectors will be. So, and how about the angles? All the angles will be equal. These angles will be omega ts. But when you go above that 1.33, you will start seeing that this average angular velocity will start changing. So, let us, as I mentioned to you, this is 95.2% and we call this as overmodulation zone 1 in the space vector modulated inverters. That is, in this case what will happen is the average voltage, the angle would vary almost linearly with time, whereas the magnitude will change. How will the magnitude change? So, it will be in overmodulation zone 1, it will be partly hexagonal and partly circular, and at m is equal to 1.33, this becomes fully hexagonal. So, up to this m is equal to 1.33, from 1.15 to 1.33 we would call as overmodulation zone 1, that is from 1.15 to 1.33. these are the values of M, you would call this. Above that we will call as overmodulation zone 2. So, now this is an example for M is equal to 2. You can see that this angle is quite long, much longer than 150 degrees now. So, if you look at this is your average line to line voltages. So, VRY is fixed to plus VDC for a long time, the same thing about VYB. So, now if you look at it here, this is VRN average and this is VYN average. So, VRN average is also not changing, I mean this is VBN average is also not changing. So, this is your VRO average and this is your VRN average, and you can see that the VRN average is here, this is 2 by 3 or 0.67, this is 2 by 3 VDC. Okay. This will be 0.33 VDC. Okay. So, you get these waveforms like this, and you will see here V alpha is equal to 1, V beta is equal to 0. So, this is a vector, voltage vector 1 is applied here, and here you will find voltage vector 2 is applied, here voltage vector 3 is applied, here voltage vector 4 is applied, here voltage vector 5 is applied throughout. What happens is gradually this expands, the time for which this expands, and it goes on increasing. Finally, only the active vectors are applied, V1 applied for 60 degrees, V2 applied for 60 degree, V3 applied for 60, V4 and V5, and once finally V6 is applied. That would what will be your 6 step mode. So, we are little ahead of 6 step mode. So, here as I told you is vector V1, vector V2, vector V3 are all applied here. Okay. So, now this is how the magnitude varies over a sector. So, initially the same vector 1 is applied, here this is active vector 2 is getting applied. So, the angle varies somewhat in a piecewise linear fashion, this is 0, this is 0, and it moves with some slope, and this slope is certainly higher than the slope if you join these two lines by a straight line. So, this angular velocity is higher than the fundamental angular frequency. So, overall whatever time the fundamental angular frequency would take, for example, if there is this fundamental vector that will move like this at a uniform velocity. Now, the applied voltage vector is initially a little slow, and then it is much faster, and finally it slows down. This is how it happens now. So, you have your vectors, how do you get them? In this region you have the active vector being applied. So, like we did before for sine triangle PWM, what you will have is, you will have, let me change it to red. So, in subcycles surrounding here, the same active vector, the average vector is equal to active vector 1, then it goes around, in the subsequent subcycles it goes around, and this angle is greater than your omega ts, this angle is greater than your omega ts, this is also greater than your omega ts. So, let us call this as some alpha S1, this is also that alpha S1. So, again when you go to active vector 2, it is applied continuously like this, and then in the next subcycles you will have vectors like that. When you come closer to active vector 3, again for the number of subcycles, the average vector applied over the subcycle will be equal to this now. So, you will have many vectors applied here and a few vectors in between in few of the subcycles. As time goes on, as the depth of modulation goes on increasing, you will have more and more of these vectors getting aligned here, and that would be 6 step operation now. So, here I have just tried to summarize that. So, it is pretty similar to what it was in sine triangle PWM when you look at m greater than 2, the same story here when you have m greater than 1.33. Okay. So, the trajectory of the tip of the vector is fully hexagonal, the angle varies in a piecewise linear fashion, and the average voltage vectors are concentrated closer to, I mean basically many of the average voltage vectors are along the active vector. That is what is the more precise statement than saying so. Now, what we can do is, if you look at the square wave operation, that is at the end. So, every phase is switching, R phase switching here at after 180 degree. So, Y phase also switches here and after 180 degrees. So, this is square wave operation. So, your VRO average is a square wave like this, and VRN average would be this, there is a third harmonic common mode you will find, a triplet frequency common mode. You subtract that from VRO average, you will get your VRN average like this, and this is your VRN average. This is 2 by 3 VDC. This is 1 by 3 VDC, this is minus 1 by 3 VDC, this is minus 2 by 3 VDC. And similarly, you will have VYN average and VBN average, they can be transformed into V alpha average and V beta average. So, V alpha average has the same shape as VRN average, and this is your V beta average. So, now what happens, what I told you before, that is for a 60-degree duration starting from here to here. So, when your fundamental voltage vector moves from here to here, all the vectors in every subcycle are applied like this. Similarly, for a 60-degree interval starting from here to here, all the vectors in every subcycle, the average voltage vector applied is equal to V2. The same story is repeated over this 60-degree interval. So, it is the same average voltage vector equal to V3 applied. So, what you have is you always have only these vectors getting applied as the average voltage vectors. This is only the same vector. So, no vector other than these 6 vectors ever get applied in any of the subcycles, and in all the subcycles in this 60 degree, this is the only vector applied. In all of them within the 60 degree, this is the only vector applied, and this is what is your 6-step mode. This is your square wave operation now. So, you can find things from this thesis, I mean this and here this paper in Sadhana journal. This talks about the analysis of sine triangle PWM and also the common mode injection PWM from a space vector point of view. Okay, this would be a good reference now. So, if you look at this in the space vector modulation, you have a reference vector like this, you have a rotating reference vector like this. So, what do? The reference vector goes on increasing, you go about increasing the magnitude of the reference vector, and that is what you do to increase your modulation. Can you reach 6 step by simply by increasing this? Probably not. So, let me say what happens now. You go about increasing this, let us say your reference vectors go like this. This is your reference vector, this is a reference vector, they are going well outside the hexagon. Can this be realized? No, they cannot be realized. So, what can be realized? What can be realized is only this part. What can be realized is only this part. So, let us say you apply these vectors. Now, what is your modulation index, or what is the fundamental voltage? The fundamental voltage would be only 95.2% of the square wave, but you have to reach 100%. So, when you are providing your 3-phase references, when you are providing them as 3-phase modulating signals, you go on increasing the modulating signal peak, it goes into 6-step operation, but here it does not go automatically into that, you need to do something. What have you got to do? You have to change your reference vector such that in these subcycles the reference vectors get shifted closer to the active vector 1, and in these subcycles it gets shifted closer to active vector 2. When you are doing space vector modulation, when your reference is specified as a voltage space vector and so on, you need a special overmodulation algorithm. Normally we have what is called as a standard overmodulation algorithm, or which is a 2-zone modulation algorithm. The zone 1 of the overmodulation algorithm can be given like this. You may have a reference, this is partly within the hexagon and partly outside the hexagon. What you would actually do is you would produce vectors like this whose tips are like this. You would produce vectors whose tips are like this. This would be called as overmodulation zone 1, and this radius of the circle we can probably call it as V circle, or we can call this angle as alpha circle. What you can see is this V circle can be used to control the fundamental voltage. So, V circle can vary between 0.866 to 1, or alpha circle can vary between 30 degrees to 0 degree. By varying this, you can control the fundamental voltage, but there is a non-linear relationship. V circle is not related to a fundamental voltage in a linear fashion as V reference was. There is some non-linear relationship. So, if you look at the voltages applied, now this is Vp and alpha p, or the magnitude and angle of the voltage vectors which are actually applied. When you are in the circular portion, you are in the hexagonal portion like here, this magnitude of the vector is given by 0.866 VDC by cos of 30 degree minus alpha p. Your alpha p is always equal to alpha reference, and this is your Vp, and when you are in the circular portion of the trajectory, your Vp is equal to V circle. So, we call this as the overmodulation zone 1 in a standard overmodulation algorithm. Now, you use Vp and alpha p instead of Vref and angle alpha, you use Vp and try to do this volt second balance. So, you use Vp and alpha p to calculate T1, and again Vp and alpha p to calculate T2, and from there you get Tz, and you could do your SPWM space vector PWM calculations now. So, when you go into overmodulation in zone 2, what do? is you have to make sure that all of them are like this. That is, as we found that was happening in sine triangle PWM, what we will do is initially for some angle we will make sure that all the vectors are like this. That is, when your reference is in this angle. When your reference is in this angle, again we will make sure that all the applied voltage vectors are like this, and in between what we will do, we will make sure that the average vectors go around like this. That is, it will follow an entirely hexagonal trajectory. The equations can be given here. Let us say we say alpha p is equal to 0 initially, when your reference is between some 0 and alpha h. So, it is alpha h, let us say 10 degrees say. So, it is 0 and Vp is 0.866 VDC by cos 30 minus alpha p. If alpha p is 0, Vp will also be equal to VDC. So, you are applying active vector 1. Again the last 10 degrees from 50 to 60 degrees, you are going to apply pi by 3 and Vp is equal to VDC. You are applying active vector 2, and in between you are changing the reference angle like this, alpha reference minus alpha h divided by pi by 6 minus alpha h. So, if it is depending on this, this is what is called as a standard 2 zone algorithm. This is what is most widely used in space vector based PWM methods, and it is very popular. So, here once again you make use of this Vp to calculate. Now, null vector is not applied, therefore, you are using only V1 and V2, and so you are using your alpha p and Vp to calculate your T1 and T2. You can actually find this standard 2 zone algorithm for space vector inverters in this. This is with this holds load scat and Kambadukone, and again this other paper written by DC Lee and GM Lee. Okay. Then there are also certain other things that you can really do. See, what happens is you do not have to follow the same algorithm as before. I have, for example, there is another algorithm. This is k ang into alpha ref. If your alpha ref is between 0 and 30 degree, where k ang is a positive number, 0 less than k ang less than 1, or let us say less than or equal to. If I make k ang is equal to 1, I am at overmodulation zone 1. I can change from k ang. If I reduce from 1 to 0, I will be able to increase thing. Now, let us say k ang is a fraction. So, what happens? All the vectors in the first half get pulled closer to active vector 1. Again, all the vectors in the second half of sector 1 get pulled close to the active vector 2. So, I will have many of my vectors like this. The first here, and again this will be more sparing here, in between it will be sparing. This is how the vectors will be, and this is actually a modified 2 zone algorithm. So, you can vary k ang from 1, you can reduce it towards 0 to achieve 6 step mode. At 0 you will achieve 6 step mode. One advantage you will get is k ang and the fundamental voltage vary more or less linearly in this. That is one advantage here. There is also what is called a single zone overmodulation algorithm. What it does is you have this circle going out and in. I am sorry for the poor circle. So, let us say it is like this. So, what you do is whenever your reference is here between these two, you apply the same vector. Whenever your reference goes out of that, for example here out of the hexagon, you continue to apply the same one. So, once again it comes back, you will apply this vector here. So, this is what is called as a single zone overmodulation algorithm. Here this V circle, when it goes to 1, you will reach 6 step mode. So, the single zone algorithm, this is the reference for the single zone overmodulation algorithm, and these two are examples for modified 2 zone algorithms. So, that they are two different modified algorithms are discussed here. There is one kind of modification based on k ang is discussed here, another modification is discussed in this one. So, these are useful references for you. So, these are some more references which deal with low switching frequency PWM. So, that is about my lecture on overmodulation methods, and I am sure the lecture these references will be useful to you. I hope the lecture was useful to you, and I look forward to your continued interest for the remaining module, that is on PWM of multi-level inverter. Thank you very much for your interest.